Good morning, class. You guys had some homework? The homework was exercise 1.5. Okay, was there any issues with 1.5? 1.5 you had to do the second column. Okay, was there any problems with the second column? Sorry? No. No issues. Then you had to do 1.6. The even numbers. Any problems there? No. That was all. Now we're looking at solving equations with rational exponents that can be factorized as a trinomial. Okay. This is on page 13. You'll see. Okay. So you're looking at example 1 on page 13. Okay, so at this point, what we should note is that, as we did yesterday, using that case substitution, that same idea is going to be implemented here. Okay. If I look at x to the quarter compared to x to the half, we know that a half can be written, or x to the exponent half can be written as x to the quarter raised to the power 2. Not so. Why? Because a quarter times 2. What's a quarter times 2? Half. Not so? Which then gives me again the first term in that trinomial on the left hand side. You will understand. So in other words, what I'm going to do is I'm going to say let k equals x to the quarter. If that is the case, what do we have here for the first term? It will be k squared, yes, minus 3k minus 10 is equal to 0. So what is this now to us? Trinomial. Okay? Factorize a trinomial. The factors is going to be 5 and 2. Do we add or subtract our factors? Subtract them. The bigger one must be negative, so it's negative and constant. You will understand at this point? What are you confused about?
I don't understand k squared.
K squared. You see, if you got x to the quarter, what I want to do is, I want to write the first term in terms of x to the quarter. Why? So that I can replace x to the quarter with an easier variable to factorize the trinomial. Okay? So what we have is x to the quarter squared is representative of x to the half. Or x to the half can be represented as x to the quarter squared. So what happens is, if I let k equal x to the quarter, then this should be simply k squared. Okay, that makes sense? So it becomes k squared minus 3k minus 10 is equal to 0, which is your trinomial. We factorize the trinomial. So what do we say now? You can say that k minus 5 is equal to 0. So k is equal to 5, or k plus 2 is equal to 0. So k is equal to negative. But what is k? X to the quarter. So what was the rule I told you yesterday with regards to the denominator being even in the exponent? Sorry? The number must be positive. Is this number positive? Yes. So what do I do is, I raise it to the exponent for both sides. Why 4? Because 4 is the reciprocal of a quarter, or 4 over 1. So that x is equal to, what is 5 to the exponent 4? 625. Again, is this, since the denominator is even, this number must be positive. Is the number positive? No. So no solution on that branch, on that solution. You guys understand? Any confusion? Let's do another example. Example 2 on page 14. Example 2, page 14. Okay, so this one will work together. Okay, so what are we going to let k be equal to here? So we say let k equals x to the third. So what will the trinomial now read? Sorry? K squared. You all agree with that? Huh? K squared minus 2k minus 15 is equal to 0. So what do we have now? Trinomial. Factorize the trinomial. So this gives us k 5, 3. What about the sign? Minus 5 plus 3. So in other words, k minus 5 is equal to 0, or k plus 3 is equal to 0. So k is equal to 5, or k is equal to negative 3. But what is k? X to the third. So x to the third is equal to 5, or x to the third is equal to negative 3. Is the numerator denominator even? No, so no restriction needed there. Or given. So I'll erase this to the exponent. 3. So x is equal to 125. Raise that to the 3. So x is equal to negative 27. Okay. Any problems there? No. Okay, in exercise 1.7, see number 1 here, the sum is already factorized. Can you see that? So here we can just say simply that x to the half is equal to 3 or x to the half is equal to 2. Then you solve for x. Can you see that, people? So in number 1, 4, 7, it's already factorized. You're looking, tell me. You understand what I'm saying here? Okay? So that's already factorized. It's from 10, 13, 16 and 19 that you still need to do the case substitution. You guys understand? For homework is exercise 1.7 on page 14, the first column only. Okay? So now we're going to look at surds. We've dealt with surds before in grade 8. I'm not sure if we've done it at primary school yet. Grade 8, grade 9 and grade 10 we looked at surds. Okay. Okay, so we're looking at surds on page 15. On page 15 we're told that surd is a number of the form a plus b, the nth root of c, where c is greater than or equal to 0. Okay? Where the nth root of c is irrational. Doesn't have to be, okay, it will result in a positive solution, but I don't fully agree with c being greater than or equal to 0. There's only when is this condition needed? When does c have to be positive? If you look at where C is lying under here. Not so. So when does, you all agree that greater than or equal to 0 means positive. When must that be positive? There we go. If n is to the power of 2, or if n is even. That's the only time that has to be greater than or equal to 0. Okay? If that is odd, then C can be negative. Okay? You all agree with that? But when you simplify, the negative will come out again anyway. Okay? Probably that's why they got it as greater than or equal to 0, where it is in the simpler form, or the simplest form. Okay? where the nth root of c is irrational. Examples of surds are 3 plus root 2. As we know, the root 2 is a surd. Okay? 5 minus root 7, the root of 3, the cube root of 4, and so on. Note that a to the 1 over n times b to the 1 over n can be written as. What do you notice there? That the exponents are the same. Not so, and we're multiplying. Then we can write it as 1 power of ab raised to the exponent 1 over n. Okay? There they're refreshing your laws of exponents that was done last year. As the nth root of a times the nth root of b can be written as the nth root of a times b. The example given is the cube root of 5 times the cube root of 2 can be written as the cube root of 10. As long as the roots are the same and is multiplying, we can multiply the numbers under the root there. Number 2, the nth root of a over the nth root of b can be written as the nth root of a over b there. The example is given as the fifth root of 64 divided by the fifth root of 2 can be written as the fifth root of 64 over 2. 64 divided by 2 is 32 and the fifth root of 32 is 2. 32 can be written as 2 to the power of 5. Then we are given in law 3 that the p root of the cube root the q root of a can be written as the pq root of a. Okay, that is the square. An example given that the square root of the cube root of 7 can be written as the sixth root of 7. Okay, and then the p root of a raised to the power q can be written as the p root of a to the q. The example given there is the cube root of 8 squared can be written as the cube root of 8 all squared can be written as the cube root of 8 squared, which is equal to the cube root of, as we know, 8 squared is 64, and the cube root of 64 is 4. Definition for n, a natural number where n is greater than or equal to 2. We know that a to 1 over n can be written as the nth root of a. Number 2, we got a to the negative 1 over n can be written as the nth root. Remember that the denominator will always be the root. Okay, so it's the nth root of a to the minus 1. And thirdly, a to the m over n can be written as the nth root of a to the m. Okay, now we're going to look at simplification of surds on page 15. Simplification of surds, page 15. Okay, so let's look at the first one. Simplifying the following expressions, write your answer in the simplest surd form where necessary. Okay, so looking at the square root of 3 times the square root of 3. What would that be? Is the roots the same? Yes. So we can multiply the numbers below. So 3 times 3 is? What's the square root of 9? You all agree with that? So what would the next sum then be? The square root of 3 times the square root of 5. Are the roots the same? Yes. So what's square root of 3 times the square root of 5? Square root of 50. Okay? You all okay with that? Now let's look at number 3. In number 3 we are given the square root of 75. Okay. So we ask ourselves, okay, what is the biggest or the largest possible perfect square that is divisible by 25? By 75. Okay, with the answer 25. Just a step back. What are perfect squares? Perfect squares is 1, 4, 9. The next perfect square? 16, 25, 36, 49, 64, 54, 64, 81, 100, 121 and so on. So the largest, we're never going to use 1 because I'm not going to make any difference. Okay? So the largest perfect square that can go into 75 without a remainder is 25. Not so. So this can be written as 25 times 3. Not so. So now, coming back to this rule here, it can be written as the square root of 25 times square root of 3. What's the square root of 25? 5 times root. That's why when you put it in the calculator, square root 75, you get 5 root 3. Can you see that? And that is how the calculator gets back. Does it make sense? But often the sum says without the use of a calculator. And that's how we do it without the calculator. Okay? You all understand? Alright. So you guys do 18. Let's see. You do 18. Okay, so 18 can be written as what? What is the largest perfect square that goes into 18 without a remainder? 9. And it's going to be 9 times 2. So that will be the square root of 9 times the square root of 2. The square root of 9? 3. So it will be 3 root 2. Alright, you guys understand? Right. The number 5 quickly. That should be simple. Square root of 9 over 9 over 4. Square root of 9 is 3. Square root of 4 is 2. Or if you wanted, you could have written as square root of 9 over square root of 4 and then get 3 over 2. Okay, it's the same thing. Let's look at number 6. What do you think is going to happen here? We need to break up the 12. So it's going to be 6 plus. What is the largest possible perfect square that is divisible by 12? 4. So I write this as the root of 4 times 3. Remember 4 times 3 is 12. Over 2. As we did before, we're going to break this up. So it's 6 plus what? This would then be the square root of 4 times the square root of 3 all over 2. Not so? At this point, I put each one over its own. So it's going to be 6 over 2 plus, what's the square root of 4? 2 root 3 over 2. Okay? So what's 6 over 2? 3 plus 2 going to 2 once, 2 going to 2 once, square root. Okay? You all okay with that? Need some practice on this, no? No problem. Now let's do 7 together. So what's the first thing we're going to do? Break up the 18. So break up the 18 quickly. Instead of breaking this up here, I could have factorized the 2 as well. Okay, this is another way of doing it. Okay, so the 18 can be written as 9 times 2 over 6. What's the next step we need to do? Root 9 times root 2. Break that up. Now what we do, we apply the square root, not so? Or we could break it up like this here. But we are rather going to apply the factorization. Or let's do both. I'm going to break it up, then you can see the difference, okay? So that's going to be 9 over 6 plus 3 root 2 over 6. Okay? What do we do thereafter? Simplify. 3 goes into 9 3 times, 3 going to 6 twice, 3 going to 3 once, 3 going to 6 twice. So you will have 3 over 2 plus root 2 over 2. So what do you notice? Same denominator, so it can be written as 1. 3 plus. What's wrong? Nothing. Okay. If, however, at this point we had taken the LCM, not the common factor, that would have simply been 9 plus root 9 root 2 over 6. So that would be 9 plus the root of 9 is 3 root 2 over 6. We take our 3 as a common factor. I'm then left with 3 plus root 2 over 6. And of course 3 going to 3 once, 3 going to 6 twice. So I'm left with 3 plus root 2 over 2, which is the same as an answer. Okay. So either way, you're going to get the full mark for this question. Okay. Any questions? Any confusion? No? So we're going to do exercise 1.8 on page 16, the first column quickly. Alright. You guys done with number 1? Yes, okay. Okay, so for 63, what's the biggest perfect square that goes into 63? Without a remainder. So that's going to be 9. So it's 9 times 7. That can be written as the square root of 9 times square root of 7, which is 3 root. You all okay with that? E for the root 45 is going to be the root of 9 times 5. That can be written as the square root of 9 times the square root of 5, which is 3 root. The biggest perfect square that goes into 32? 16. It will be 16 times 2, which is square root of 16? 4. 4. Now say for argument's sake, you went and said for the root of 32, it could have been the square root of 4 times 4 times what is 32? 8. So that would have been written as the square root of 4 square times the square root of 8, which is 2 root 8. Not so? But you see there's another a perfect square that can go into 8 again. Not so? So then you must go take it further. So that's going to give you 4 times 2, which is 2 root 4 times root 2. Square root of 4 is 2. So it's 2 times 2 root 2, which is 4 root 2. Which is the same. It will take you a bit longer if you don't see the biggest perfect square. But if you had gone that route, it's just an extra 2 steps, 3 steps that needs to be added. Okay? Let's look at number 2. Guys, finish with number 2 as well? No? They're dealing with perfect, the fourth roots and cube roots in this case. So 81 is a perfect cube. Did you guys get it?
Any mathematicians?
Hi boss,
Good.
good.
I'm good. I wanted to ask when there's a number. Do you have a textbook?
Textbook.
Okay. Okay, shukran.
Afwan. Okay. People, 81 is a perfect cube. This can be written as 3 to the 4. Not so? The fourth root of 3 to the 4. So that would simply be 4 over 4, which is 1. Not so? 27, the cube root of 27 is 3. Or we can say it's a cube root of 3 cubed. 3 over 3, which is 3 to the 1. The cube root of a negative will always be negative. As a cube root of 8, 2. As a cube root of 125. Okay, you guys understand? Let's look at number 3. Write the following in the simplest surd form without the use of a calculator. I'll give you a couple of minutes to do the sum quickly. These 3 sums. Okay. The first one can be written as 3 times 12 can be broken up into 4 times 3. So that can be written as 3 root 4 times root 3. What's the square root of 4? 2. And 2 times 3 is 6 root 3. Okay, you look over that. Don't forget you're writing one below the other. Okay? Just because of space here, I'm writing it like that. Okay? 8 can be written as what? 4 times 2 over 2. So that would be 4 plus root 4 root 2 over 2. What's up? So that will be 4 plus, what's the square root of 4? 2. So 2 root 2 over 2. each one of its own. So it's 4 over 2 is 2 plus 2 root 2 over 2 is going to be root 2. You all okay with that, people? You all okay with that? Any confusion? None? And the last one, I. What is the biggest, or the largest perfect square that's divisible by 98? Sorry? 49. So 49 times 2 over 40. So it's going to be written as 21 minus the root of 49 times the root of 2 all over 40. So it will simply be 21 minus, what's the root of 49? 7 root 2 over 4. Okay, put each one of its own, or I can factorize. Well, factorize. What is common in the numerator? 7. So I'm left with 3 minus root 2 over 40. Now what? You cancel. 7 going to 7 once, 7 going to 40 twice. So it's 3 minus root 2 over 2. Okay. Any confusion? No? Right. For homework? I would like you guys to do exercise 1.8. We have done the first column. I want you guys to do the second and the third column for homework. Second and third column for homework. Okay. And that's very important for tomorrow's lesson. Alright. Guys can start with your homework now. Tomorrow's lesson. Did I say test? Would you like to write a test tomorrow? That's a very good idea. Alright, you guys can start with the homework.